Welcome back, everyone. It is my great pleasure to introduce Euan Spence from the University of Bath, who will give a talk at the analysis seminar today. He will be talking about, his title is the following: For most frequencies, strong trapping has a weak effect in frequency domain scattering. So, Euan, the floor is yours.
Thank you, Matteo. Yeah, thanks for the invitation. So I last gave a seminar in Cardiff on Halloween in 2016, so almost exactly four years ago. And so it's a pleasure to be back, albeit virtually. So that's the title of my talk. This is joint work with my postdoc, David Lafontaine, here in Bath, and Jared Wunsch, who's a professor of maths in Northwestern University in the US. And so I should say that this talk is based on a paper with the same title as the talk, and you can find, if you want to find this paper later, just go on any of our web pages, you'll find links to it, etc. Okay, so the general area of the talk, and indeed what I spend most of my mathematical time thinking about, is questions to do with the analysis and numerical analysis of the high frequency Helmholtz equation. And the plan of this talk is it's got three parts, A, B, and C. And the first is a question in analysis that I'm gonna pose, and I'm then going to briefly, in the second part of the talk, indicate why I was interested in this question, and it's motivated by numerical analysis. So I'm going to have part B is then why interesting for numerical analysis, and part C of the talk is then the answer to this question. But of course, this is not a numerical analysis audience, and so I don't want to scare you. There will just be 2 slides or 1.5 slides on the numerical analysis aspects. But it's mainly about analysis. Okay, so the boundary value problem I want to start considering is this very famous problem involving the Helmholtz equation. So I've got the Helmholtz equation here, excuse me, and I'm posing it outside some impenetrable obstacle. So I've got some obstacle here, on which I'm imposing a Dirichlet boundary condition. So my solution of my Helmholtz equation, U, is going to be 0 on the obstacle. Then there's some source function f in my equation, and the support of f is compactly contained in RD. And here's the support. And so my task is to find U satisfying the Helmholtz equation with this f on the right-hand side. And then because the domain I'm posing this problem is unbounded, I've got then this radiation condition at infinity here. So from the mathematical point of view, this is a condition at infinity to ensure that the problem is well posed. And from the physical point of view, this is a condition that says that waves, so it says that our source F is creating some waves, they hit the obstacle and then scatter off, but we don't get any waves coming in from infinity. Okay, so that's the physical meaning of this radiation condition here. And this K that I'm highlighting in blue, this is the frequency or the wave number. And I'm interested in the case when K is large. And also I want to make things explicit in the frequency. So everywhere in this talk, K is going to appear in blue. Okay, and so it's a very classical result due to relic that the solution of this problem exists and is unique. And after you've established existence and uniqueness, the most basic PDE question after that is, does the solution depend continuously on the data? So in particular, is there some constant C such that some norm of U is bounded by some norm of F? And here I've been deliberately vague about what norms of U and F I'm considering, but I'm going to be very concrete in a minute. And so this constant C, I'm going to call, to distinguish it from other constants, I'm going to call C sub res, where this res subscript stands for resolvent. And the reason for this is that if you remember from your functional analysis class, that the resolvent of an operator, P, is then the inverse of P minus Z. And when this exists, Z is in the resolvent set. So if P is the minus Laplacian and Z is K squared, then the resolvent of the Laplacian is the inverse of the Helmholtz operator. And so because of this, such bounds on U in terms of F are often called resolvent estimates in the literature. So this C sub res is standing for this, res stands for resolvent. Okay, and in the rest of the talk, C-res is going to be my main object of interest, and so I'm going to highlight it in red. Okay, so I was a bit vague about what norms I chose, but now I'm going to be more precise. So here's this scattering setup again, and I'm going to take some big ball of radius r that contains both the obstacle and the support of my right-hand side f. And I'm going to measure then both the data and use norms on u and f that are L2 in this big ball. Right, so I've got R such that it contains the support of F and the obstacle, and I'm then having L2 norm of F in this big ball, and the L2 norm of U in this big ball on the left. And now I'm going to be careful about what this constant C-res depends on. Okay, so I've been calling it a constant because it doesn't depend on U and F, but of course it depends on other parameters in the problem. So the first of these that it depends on is R. Okay, it depends on capital R because if I make capital R bigger, then since F has just got compact support, the norm of F then doesn't get bigger with R, but of course U has support everywhere in the exterior, and so if I increase R, then this left-hand side must increase. So if I increase R and the left-hand side increases, but this norm of F here doesn't increase, it means that C-res has to depend on R, and in particular has to increase as R increases. So what else does this C-res depend on? Well, it depends on the frequency K that I'm indicating here in blue. And so I said that I was interested in high frequencies. And so what I'm going to do is, so you can give me your favorite or some lower bound K0 on frequencies, and I'm going to consider all frequencies higher than that. And this is just to avoid the sort of studying the low frequency behavior, which is a bit different to the high frequency behavior. So we've got C-res depending on K, K0. Okay, still on R, and the final thing that it depends on is the obstacle that I'm denoting by O itself. Okay, so this is the setup. I'm interested in understanding this constant or rather function C-res that's a function of all these things. So up till now, I haven't been very careful because I haven't actually established that. Sorry, I haven't been very careful. So I haven't established that C-res exists, but actually the same Fredholm theory that gives you existence and uniqueness of the solution U tells you that such a C-res exists. So also since Cardiff have got this very fancy version of Zoom that involves the mind reading feature, I can read some of your minds, and you're all thinking, come on, Euan, U is the solution of a second order linear elliptic PDE, and so the natural norm to measure U in is like the H1 norm, right? The energy norm. So why are you only measuring the L2 norm on the left hand side? But so to you people who are thinking this, I would say, don't worry, because it turns out there's a simple argument involving Green's density that says that the L2 norm of the gradient of U is bounded by K times C-res times the norm of F, and so therefore I can form this weighted H1 norm, and then that's bounded again by K times C-res. So in summary, if I have then this, if I know C-res that's in this L2 to L2 bound, I can get an L2 to H1 bound, from this. Okay, so there's no problem in just considering the L2 norm of U. Okay, and also, so up till now I've considered the case where the data from the problem is coming from some compactly supported F that's generating the waves, but I could also consider having some non-zero boundary condition, so a non-zero Dirichlet boundary condition on the obstacle, and having the waves somehow generated by that. And in that set of a natural object to study is the Dirichlet to Neumann map that takes the Dirichlet data on the obstacle to the Neumann data on the obstacle. And it turns out that there's a sort of general recipe developed in a series of papers that show you how to get from a bound on the C-res can get you a bound on the Dirichlet to Neumann map. And in fact, here it is. It's if your Dirichlet data on the obstacle is in H1 of the boundary, then your Neumann data is in L2 of the boundary, and you have this bound here where this constant here only depends on the obstacle. Okay, so the moral is I'm just going to talk about C-res that appears in this L2 to L2 bound here, but other natural objects of study for this problem, such as the Dirichlet on a map, that you can study their dependence on, in particular, K by knowing C-res. Okay, and so as I noted earlier, somehow Fred arm theory tells you that this C-res, such a C-res exists, but it doesn't tell you any information about how C-res depends on the frequency K or on the obstacle O. And that's what we're going to now talk about now. So to explain this dependence, I have to remind or recall the definitions of trapping and non-trapping in this obstacle setup. So here's an obstacle, and the algorithm for determining if you're given an obstacle whether it's trapping or not is you first draw a big ball of radius r, and inside that ball you consider all the rays coming from every point. Okay, so here I've drawn a few of them, and then you continue these rays they're in straight lines because the wave speed is constant outside the obstacle, and you then continue the rays when they hit the obstacle using this kind of angle of instance is angle of reflection rule that you learned at school, right? You draw your normal and angle of instance, angle of reflection. This then tells you how to continue the rays. So you do this for all the rays starting at every single point, all the rays going in every single direction. And if all these rays escape from the big orange ball in some uniform time, then the problem is non-trapping. So let's take another example. So this obstacle here, if I do the same thing, then this ray here starting at this point, it just bounces back and forth here. So this is not non-trapping, and therefore it's trapping. Okay, and so this is exactly sort of corresponding to our physical intuition about kind of cavity-shaped domains trapping high frequency waves. And so yes, so these are the conditions about rays. And again, it's natural that the high frequency behavior of the solutions of the Helmholtz operator, Helmholtz equation, depend on rays, because this whole notion of geometric optics, right? Geometric optics tells you that the high frequency behavior of waves is dictated by the rays, and there's a large amount of mathematical literature sort of justifying that, some of which we're going to see now. Okay, so now in one slide, I'm going to tell you what is known about C-res in this setup of this obstacle problem. So here, just at the top, this is the reminder of the definition of C-res. And the first result then is if there's no obstacle, or if the obstacle is smooth and non-trapping, then C-res depends on K, so it goes like 1 over K. Okay, and so more precisely, there's some function C tilde of K naught obstacle and R, and C-res is this function of C tilde over K. Okay, and so I'm just going to abbreviate this behavior as sort of twiddles 1 over K. Okay, and this is a very classical result. Somehow it relies on these deep results about propagation of singularities by Melrose and Shostrand. I should also say that actually in some other recent work with Jared Wunsch and also Jeff Galkowski from UCL, we sort of worked out exactly what this function C tilde is. Okay, it turns out that when the frequency K is large enough, this C tilde is actually the length of the longest ray in this ball of radius r. Okay, so it's a function of the ball and also the obstacle. Okay, and so note that I said if the obstacle is smooth and non-trapping. So of course, and in these examples where I show this algorithm of determining whether the problem was trapping or non-trapping, if you see, my obstacles are smooth because I didn't want to get into the issues about what happens when there are corners. And so life, of course, is not too short to think about these things, but this talk is. So I'm just going to focus on the smooth case of smooth obstacles, at least in stating this non-trapping result here. Okay, so when things are non-trapping, C-res goes like 1 over K. What happens when the problem is trapping? And then there are 3 different types of trapping, and here are the sort of prototypical examples of each of them. So here on the left, we have the weakest type of trapping, which is called hyperbolic trapping. And the standard example is like two circles in 2D or two balls in 3D. And you see there's one trapped ray, here it is, but if I perturb it slightly, then I escape very quickly. So it's very unstable trapping. And on the other extreme, the strongest form of trapping is called elliptic trapping, and that's on here on the right. And you see here I have this trapped ray here, and if I perturb it, then I just still bounce around here. It's very stable trapping. Okay, and this dashed red, this dashed red line is the boundary of an ellipse, because you can prove some nice things in this situation, which we're going to come to in a minute. And so in this kind of the weakest possible form of trapping, C-res goes like log k over k. So you get this logarithmic increase compared to the non-trapping estimate. Okay, non-trapping 1 over k. Then in this weakest case of hyperbolic trapping, log k over k. And in contrast, in the strongest form of trapping, this elliptic trapping, C-res can grow exponentially in k. And somewhere in the middle, there's this case of parabolic trapping, the prototypical example of which is 2 squares. And here you get some polynomial increase in k compared to the resolvent, to the non-trapping resolvent estimate. Okay, and I should say, so this is so there's lots of work by Ikawa on this problem of scattering by many convex obstacles. This result here was proved by Nicola Björk. This is also Björk. And then this is Simon Chandler-Wild. This is myself. This is Andrew Gibbs, and Valery Shmizlayev proved this result here. Okay, so now I want to focus on the case of elliptic trapping. So go deeper into this case. So what do I really mean when I wrote C-res twiddles e to the alpha k? Well, so the first thing is there's this result by Björk saying for any smooth obstacle, C-res is bounded by e to the alpha k. So i.e., if you give me any f you can give me that's got support in this ball of radius r, the L2 norm of u is bounded by e to the alpha k times norm of f with some omitted constant that doesn't depend on k. And this is for all k sufficiently large. Okay, so this is just me spelling out again what our definition of C-res was. And I should say, because I'm primarily interested in the case of the k dependence of C-res, you see here I've written C-res and I've abbreviated, like I haven't put that it depends on k naught and depends on obstacle and depends on r, right? I'm just to save space, I'm just going to write it depending on k, because that's what we're primarily interested in. Okay, so that's this upper bound here, and Björk in the paper that he writes the upper bound, he says it's certainly also possible in the case of elliptic trapping to construct examples where this bound is sharp, but then in true French analyst fashion, he leaves this as an exercise for the reader, and so this exercise was completed by these authors here coming from the numerical analysis community, so Timo Becker, Simon Chandler-Wild, Ivan Graham, Steve Langdon, and Margot Lindner. And they took the particulars, so in the particular case of this 2D obstacle where you really have, where the boundary contains, so the boundary obstacle's got to contain a neighborhood of the minor axis of this ellipse. Then using results about eigenfunctions of the ellipse and exponential localization of these, you can show there's a sequence of k's tending to infinity, and sequence of data fj, such that then uj, the corresponding Helmholtz solutions, grow exponentially through that sequence. Okay, and there are then more general results. So for more general obstacles, more general elliptic trapping, sort of again, it's exponential growth with k to some power less than 1 by Cardoso and Popov, following earlier proof of superalgebraic growth in these elliptic trapping general cases by Popov. Okay, so I said the first part of my talk was there was going to be a question somewhere. So, and here it is. We have that in general, so C-res of k is bounded exponentially in k for all k, and there's some sequence in this case, in this elliptic trapping case, there's some sequence of k's such that this bound is achieved. But the question is, how does C-res of k behave when k is not one of these bad kj's? Okay, so when I have elliptic trapping, I do have exponential growth through the bad kj's, but what happens when I'm not at these bad kj's? And so this is a very natural question. But perhaps surprisingly, it wasn't seriously considered by the analysis community. And we're going to talk about that a bit later. Okay, but that's the question. That's our question for our talk that we're going to answer. Okay, so first part done. So now just very briefly, I want to give you 1 or 2 slides on why I came to think about this question. So the question is then who cares? Well, so I thought, who cares about C-res of K? And the answer is many people. And so here is this is a screenshot, in some sense, from our paper, where, well, so I hedged my bets and I wrote non-exhaustive list of papers, but I tried to really get as many papers that were published at the time on the frequency explicit convergence analysis of numerical methods for solving the Helmholtz equation, which then use this non-trapping resolvent estimate. So there's a big long list of things and lots of different methods, finite element methods, least squares methods, integral equation methods, all somehow using this in the analyses, this non-trapping resolvent estimate. And of course, this is completely natural because these numerical methods are, in some sense, approximating the solution operator of the Helmholtz problem, and C-res of K is dictating how that solution operator depends at high frequency. So if you want to understand how your numerical method behaves at high frequency, it's completely natural that the behavior of C-res of K is going to influence that. So I want to give just 2 examples of then how C-res of K enters into these numerical analyses of these Helmholtz equations. And I want to just give it, so the simplest example, the H finite element method, so FEM stands for finite element method, and HP finite element method. So very quickly, I'm going to just say what these are. So I've got my scattering problem here. Here's my obstacle O, and I want to solve it. I've got the Helmholtz equation posed in the exterior, and I want to approximate the solution of this. So what you do is you one way, the finite element method way, is to chop the domain up into lots of little pieces. Okay, so the first problem is the domain is infinite, so we've got to sort of truncate somehow, but let's not worry about that right now. We do some clever truncation, and then I have my domain is then, I've got some mesh on my domain. I've split up into lots of little pieces, and each of these pieces has like width proportional to h, or the linear length scale is some parameter h, and I'm going to approximate the solution on each piece by a polynomial. So I have a polynomial of degree p. Okay, and how I can how can I get a better approximation? I can like decrease h and keep p fixed, and that's what's called the h finite element method, or I can keep h fixed and increase p. That's called the p finite element method, or I can do both at the same time. I can decrease h, increase p, and that's called the HP finite element method. Okay, and it turns out that the h and the HP ones are somehow the most popular. Okay, and so if you're a numerical analyst and you're doing an error analysis, then somehow the gold standard of the thing to prove is that your method is quasi-optimal. And if you're in the Helmholtz world, you want it to be K independent. So I want to prove this bound. So this is the quasi-optimality bound, this pink star. So it's saying, so on the left here, this is now the error. So U is my true solution, and U FEM is my solution approximation by the finite element method. And I'm measuring it in this weighted H1 norm that we saw earlier, and that's not so important. And this bound is saying that the error I incur in approximating U by U FEM is less than, so less than twiddle, so up to some constant, it's less than the smallest possible error I could hope to incur in approximating U by elements of my piecewise polynomial space that I'm denoting by sort of V capital HP. This is my piecewise polynomial space. It depends on the H's and the polynomial degree P, and this is then some element of this. Okay, so that's the kind of gold standard. If you're a continental European numerical analyst, you don't start to code up your method until you've proved somehow this quasi-optimality bound. Okay, so in this Helmholtz situation, for the H version of the finite element method, in his PhD thesis, Marcus Mellink proved then this bound here that says I need HK squared to be less than or equal to some constant over K times C res. for us to have quasi-optimality. And then for the HP version in later work, so Marcus and then Stefan Zauter proved then that I can have this is quasi-optimal if I have hk over p is less than or equal to some constant, and my polynomial degree is going to grow, okay, like log k squared c res. Okay, so in the case that things are non-trapping, we saw earlier that c res was like 1 over k, right? So as we're in this bound here, k times, it means if the problem is non-trapping, k times c res is a constant, and this is saying, okay, hk squared sufficiently small, and in fact that's what you see in practice. That's then somehow sharp. And in this HP stuff, okay, c res being 1 over k means this is now a log k, and says, okay, I need hk sufficiently small and p growing like log k, and you see again in numerical experiments that's somehow what is necessary. Okay, so the point is in the non-trapping case, you stick in the known things about c res and you get results that really do correspond to reality. But now, if we think about, we want to prove a result for the trapping case, all we've got in the general elliptic trapping case is that c res grows exponentially in k. Okay, and so here I have this c res would be at e to the alpha k. Okay, and so actually this would mean that you've got to take an exponentially increasing number of degrees of freedom per wavelength in your method, and somehow no numerical analyst has ever done a computation with an exponentially increasing number of degrees of freedom in their method, or at least if they have, the reason we haven't heard from them is that they're still doing this computation. Okay, so somehow this is, unfortunately, when you put in the bound for elliptic trapping in here, you get a result that's sort of completely divorced from what actually happens in practice. And so here now, if we're in this HP method, then if I put c res going exponentially in k, okay, I get p growing linearly in k, which is not a complete disaster, but is still, again, is still divorced from somehow what people actually do in practice. Okay, so my personal motivation for working on this problem, or asking this question, how does c res of k depend on k when k is not one of these band frequencies, was to rescue numerical analysis from always having to assume that the problem is non-trapping. Okay, in all these numerical analyses of the Helmholtz equation, everyone's got to assume it's non-trapping, because if you use this exponential bound here, things are just a disaster. Okay, so that was my motivation for asking this question. Okay, so that's the end of the second part of the talk. And now in this last part of the talk, I'm going to give you the answer to the question. Okay, so firstly, just to start us off in this part, I've just reproduced this is exactly the slide we saw before, where we had the Bjerk bound, the upper bound for all k. We said this bound was sharp through some sequence, at least for this particular elliptic trapping setup. And at the end, I introduced this question: how does c res behave when k is not equal to kj? And I said that this question was not seriously considered by the analysis community. And I was careful with my words there, because the question was considered by at least one analyst. And I know this because that analyst was Jared, and he considered it when I asked him his question. So in September 2018, David and I went to visit Jared in Chicago. In normal times, in the old normal, I used to go every year to work with Jared in September. And so on one of these visits, I asked Jared this question, and Jared gave me a one-line. He thought for about 10 seconds, and he gave me a one-line answer. And I'm gonna, in a minute, I'm going to tell you what that answer is. We're going to need to do some preparatory work so you can understand it. So the first thing we're going to do is we're going to change our model problem slightly. So up to now, we've been considering the scattering of waves by impenetrable obstacles, right? This obstacle here, the waves couldn't get inside the obstacle here. But now we're going to shift slightly and consider a scattering of waves by penetrable obstacles. And so the way to model this is you have some function n that's positive function. It's equal to 1 outside some bounded set, and then the support of 1 minus n is then a penetrable obstacle. And so this n is related to the refractive index. And so then the problem is to solve the Helmholtz equation in the whole space now, including inside this obstacle. And there are some transmission conditions on the obstacle that U and its normal derivative are continuous. But then these conditions plus the PDE plus the radiation condition, this is a well posed problem. Okay, so now we're going to just consider this problem for the next bit of the talk. And why I'm doing that is because it's easy, or it's easier to actually show you some examples of elliptic trapping. Okay, so here is elliptic trapping by a penetrable obstacle. So in this case, I'm taking the penetrable obstacle to be a ball. Okay, so it's just the ball in 2D, and I'm taking the case where n, my parameter related to my refractive index, is 100 inside the ball and it's 1 outside the ball. And here on the right, then this is then one of these trapped waves. And the reason I've chosen a ball is because, of course, in the ball I have separation of variables. I can write my Helmholtz solution as a Fourier series where the coefficients are given in terms of Bessel and Hankel functions. Okay, that these are not, the understanding the high frequency behavior of Bessel and Hankel functions is difficult, but it's somehow something's been studied for a while, and in particular in MATLAB you can compute these to high accuracy. So these computations were done by Andrea Moiola for one of my papers with Andrea on the transmission problems, and he's computing then the solution to high accuracy using the fact you can compute solutions of Bessel and Hankel functions to high accuracy. Okay, and so here we have this wave that's somehow trapped round the boundary of the obstacle. So I don't know if you can quite see, but there's a thin red line that's the boundary of the obstacle, and you can see the wave is mostly sort of trapped inside, but also there's a little bit of the wave outside. Okay, so it's a bit harder in this penetrable obstacle case to understand why the trapping happens, right? Because in the sort of impenetrable obstacle case, we can all imagine some cavity and rays bouncing back and forth and getting trapped. How should you think about the penetrable obstacle case? Well, it turns out you can also understand this using rays, and you just need to go back to your high school physics. Okay, so remember at school you studied the transmission of light when it hits an air-water interface, or air and glass. I think we did glass at my school. So in air, the speed of light in air is faster than it is in water, and because n, this parameter is related to 1 over the speed, it means that n is smaller in air than in water, and then it means that the ray bends away from the normal, and somehow you get to this critical angle, and then after which you get total internal reflection. Okay, and you see this situation I'm considering up here is n is larger inside the obstacle than outside, so it's like a water, an obstacle made of water inside just air, and you see that from school you know that you can get this total internal reflection, and it's precisely that mechanism that's causing these high frequency waves to get trapped around the boundary of the obstacle. Okay, so that's to sort of give you some intuition about what elliptic trapping looks like in this penetrable obstacle case. Okay, so this slide is called Why One Expects C-Res to be Bad When K is Not Kj. And we're going to end up on the last line of the slide, where I'm going to then tell you what Jared's answer was to my question, how does C-Res of K depend on K when K is not one of these bad frequencies Kj. Okay, but then first, I'm just going to have a diversion into the asymptotics of the eigenvalues of the Laplacian on some compact domain here, right? So omega is some bounded compact domain, and so here's then the Laplacian eigenvalue problem that I'm sure you're all familiar with, and there's been a major object of study to do with the Laplacian eigenvalue problem is this counting function. Okay, so n of capital lambda is the number of eigenvalues little lambda that are less than or equal to capital lambda. And there's a huge, rich history of work on this problem and on the asymptotics of the counting function as capital lambda tends to infinity. But in particular, in this obstacle case, then you have these asymptotics as lambda tends to infinity. So I should say the first term of the asymptotics, this is somehow well known, but then there's all this work on sort of proving the sharp remainder, which in this bounded case was proved by Seeley in 1978. Okay, so why am I telling you this? Well, in our penetrable obstacle situation, we can also consider a counting function of these bad frequencies kj, right? These bad kjs are the ones for which the solution operator blows up exponentially, and I want to count these. So this is now my counting function, n of capital K. And these bad kjs are related to the resonances of this problem. So without going into too much detail, if you know about resonances, these bad kjs are essentially the real parts of the resonances. And in this kind of area of this rigorous analysis of wave problems, in the context of semi-classical analysis, there's this huge then sort of literature and research direction in taking all the results that are known for eigenvalues of the Laplacian on compact domains and trying to prove the same thing for resonances, but it's much harder. And but therefore it means we can sort of hope for or expect that the counting function of these bad kjs goes like k to the d, where d is the dimension, plus some error term, okay? And somehow this is in exact analogy with the Weyl law for the eigenvalues of the Laplacian, where here I have a lambda to the d over 2 here, and I have a capital K to the d, because somehow my Helmholtz frequency is kind of lambda is k squared. Okay, so that's why I have these different powers here. Okay, so like I said, it's much harder to prove these results about counting functions of resonances and bad kjs, but actually this result here for the penetrable obstacle case was almost proved by Cardoso, Popov, and Vodev. Okay, so almost, because they have any power a little bit, so it's k to the d minus a third plus epsilon. So any power a little bit bigger than k to the than d to the minus a third. Okay, and somehow, but if I have this counting function relation, what this implies is it implies the number of kjs in some interval of unit 1, so capital K to capital K plus 1, this number is going to go like capital K to the d minus 1 as capital K goes to infinity. So i.e. the bad kjs are getting more dense for large k. Okay, that's what this, okay, that's what these sort of heuristics that I'm telling you based on the fact we expect the resonances to obey this Weyl law is telling us. It's telling us the bad kjs are getting denser for large k. Okay, so now we've arrived at the point where I can say the one-line answer that Jared gave me when I asked him this question. I said, how does C res of k depend on k when k is not one of these bad kjs? So Jared thought for about 10 seconds, and he said, well, you have exponential blow up through the kjs, and by the Weyl asymptotics, you know that the kj is getting denser for larger k, therefore you can't expect anything better when k is not kj than this exponential growth. Okay, so that was Jared's answer. But now on this second slide, on this next slide, we're going to see that yes, it is true the bad kjs are getting denser, but there's this second effect that somehow was not appreciated by the analysts that mean that you might even expect k-res to be good when k is not equal to kj. Okay, sorry, I've just changed my slide, but it's not changing on the screen. So let me just actually stop the sharing and restart it, just because it's somehow frozen. Okay, I'm getting a nod from the chairperson. This is sensible. Okay, so I'll leave you on this cliffhanger, right? The next slide is going to be why one expects C res of k to be good when k is not equal to kj. So you can think about why that could be true. Okay. Okay, good. I waited with my heart in my mouth there. Okay, but we're on the slide now. Why one expects C res to be good when k is not equal to kj. Okay, so here we have, so the first two of these pictures you've seen before, right? This is my ball with n is 100 inside the ball and n is 1 outside the ball. And this was this picture that I was a bit vague about what this was. I said, oh, this was the trapped wave. And so what actually it is it's a picture of the scattered field when I send a plane wave in from the top right-hand corner. And this is the scattered field at one of the bad kjs. And then this third picture that you're seeing for the first time, this is also the scattered field, but now when k is not one of the bad kjs. Okay, and I should say that in this picture in the middle, the yellowest yellow is 3000, and in this picture here, the yellowest yellow is 3. And so you can see then that I'm getting massive, so that there's massive concentration of the solution around the boundary here, whereas here this scattered field in this far right picture is much more diffuse. So now let me tell you what the particular kjs are corresponding to these solutions. So here they are. So in fact, so this is again just to emphasize, we're in the ball case. We can compute actually the bad kjs to high accuracy using the fact we can compute, albeit with difficulty, but can compute about zeros about Bessel and Hankel functions. So here is one of the bad kjs, and then the point is this third picture is the k in this third picture agrees with the k in this second picture up to I think the 13th. So the first 12 digits agree, and the 13th digit is different. You see. And you see, I make this very small change to k, and this trapping behavior here that we see in the second picture completely collapses. Okay, so this second feature that I was trailering, I was mentioning earlier, was that yes, you do have very bad behavior at the bad kjs, but this behavior is extremely sensitive to being exactly on these bad kjs. Okay, and you have a small perturbation, and it completely collapses. Okay, so to give you some other numerical evidence of this, and with all these computations done by Andrea Moeller, so here on this bottom left picture, so here this x-axis here is k on a linear scale, and this y-axis you can think of this as c-res. We're basically plotting c-res of k against k, and it's on a logarithmic scale. Okay, and here Andrea has chosen a sequence of bad kjs. He hasn't chosen all of these bad kjs, he's just chosen some of them. So, and these correspond to these points here. And because you have a straight line on this graph, because this y-axis is logarithmic, this is then verifying exponential growth through the bad kjs. And these other points are just then 3 equally spaced points between each of the chosen bad kjs. Okay, but of course, I told you earlier that bad kjs are getting more and more dense, and we certainly are not looking at all of them here, but somehow we don't see any influence of the other bad kjs in these points here. And then on the right here, this is now Andrea plotting the solution, so it's the same thing, frequency on the x-axis and c-res on the y-axis, but this is at just evenly spaced points in k. And so we see again no bad behavior here. And so I should also say this picture on the left is truncated, or the x-axis goes up to k as 8, whereas this one goes up to k as 10. And the reason the one on the left is stopped at k as 8 is actually after k is 8, you can no longer see the exponential growth. Right? This graph goes up here and then it just sort of stagnates because again, the behavior of the solution operator with respect to k gets so sensitive that we can't even resolve the bad kj sufficiently well enough to reproduce this exponential growth on the left. Okay, so this is the feature, right? That we have exponential growth through the bad kjs, but it's tremendously sensitive to being actually on the bad kj. So the picture is somehow the solution operator has got these peaks, and these peaks are exponentially big, and there are more and more and more of them, but the width of the spikes are shrinking, and somehow these two factors then compensate each other and mean that actually for most frequencies you don't have a bad behavior. And I should say that this feature of the widths of the spikes decreasing as the frequency increases, this is sort of well understood in the physics community in sort of toy 1D model problems. So if you look at the Feynman Lectures in Physics, Volume 1, Chapter 23 on resonances, you'll see some kind of simple 1D example where, again, he demonstrates this, but somehow it's not this feature was not sort of more widely understood for these more general scattering problems. Okay, so here's the answer to the question: how does c-res of k behave when k is not one of these bad frequencies? And I'm going to give you the theorem in a minute, but first is here's the theorem in words. So it's that even in the presence of elliptic trapping, that's the strongest possible trapping, outside a set of frequencies of arbitrarily small measure, the resolvent is always polynomially bounded. Okay, so and here is actually the theorem stated properly. So given k0 greater than 0, okay, this is just our low frequency. We're just saying we're interested in high frequencies, and delta greater than 0. Okay, so this is now going to be our parameter controlling the set of frequencies we exclude. There's some constant c, depending on k0 delta in the dimension, and a set j with a measure of, and so this is a set of frequencies, and the measure of this set is less than or equal to our parameter delta, such that when I'm outside this set of frequencies j, I have that c res of k is bounded polynomially in k, in particular is bounded by c times then k to the 5d over 2. Okay, and if I make my delta, my set of excluded frequencies smaller, then this constant c blows up, but the k dependence stays the same. And somehow, so that's the theorem. And then, even though this pink sentence above summarized it precisely, it was a bit too long for a paper title, and so we then abbreviated this a bit more to the title of the paper. And this talk, which is for most frequencies, strong trapping has a weak effect in frequency domain scattering, where the weak effect, the point about this weak effect is that we saw earlier that somehow these polynomial increases in these weak trapping situations, you had the C rows were bounded polynomially in K. Okay, so since this talk is being recorded, I'm going to say that actually I did lie to you slightly. That there's an additional parameter, because we can't quite get k to the 5d over 2 here. We have to get any power a little bit bigger than 5d over 2. Okay, so there's some other parameter epsilon here, just in case you go to the paper and you say Euan was lying to me, but this is the honest thing. Okay, so I have some other thing. I can get any power of k a little bit bigger than 5d over 2. Okay, so that's the theorem, and I want to make just four remarks, and then we're going to be done. And so the first one is that even though I talked to you about these obstacle scattering problems, so the impenetrable one to begin with, and then the penetrable one a bit later, this result is proved in the framework of black box scattering, which encompasses many different scattering problems. And so Dirichlet and Neumann obstacles, variable coefficients, scattering by a potential, all these sort of things. So actually the main result holds for a very general class of scattering problems. So the second remark is the proof uses sort of 3 now standard tools from semi-classical analysis. So these are upper bounds on the number of resonances. I said before, this was a really kind of a very that lots of research effort have been expended on determining these bounds. And there's bounds on the resolvent away from resonances. And this nice there's the complex analysis maximum principle applied to these problems in the semi-classical maximum principle. So the point is that although putting these 3 things together and proving the main theorem was quite technical, the novelty was not so much in the techniques we used, but in asking this question to begin with about how C res of K depends on K when you're not one of the band frequencies. Okay, so the third remark is, a good question is, what is the sharp value of this exponent, right? Where we showed that C res of K was any power of K a little bit bigger than 5d over 2, but what's the sharp value? And so we worked quite hard in the case, so we chose the case, if you choose the case when the obstacle is a penetrable ball and you're in 3D, then you have sort of as much information as is currently known about the distribution of resonances, and because it's a ball, you have a lot of symmetry. And after working quite hard, we could show that C res of K was bound by K to the 6 plus 1/6. But actually, the thing we had to begin with, so 5d over 2, was then somehow K to the 7 plus a half. So any power bigger than 7.5. And we got down to 6 plus a 6. So this is a very kind of meager increase, not very impressive. And so then there is this open question of what is the sharp value of the exponent. And the final remark is that Yves Capdebosc proved some results sort of along these lines. And it's important to say that the existence of Eve's results was a real motivating factor for us. In fact, in this initial trip to Chicago, David and I were there for 2 weeks. And the first week we spent going through Eve's results very carefully, because Jared didn't believe they were true, because he didn't believe that C res of K could be good when K is not Kj. So the first week was then going through Eve's results and convincing Jared they were correct. And somehow once we'd done that, then the second week was spent proving the theorem. But it's important to emphasize that Eve's results were a real kind of important guide for us in this direction. So Eve was considering the case when the obstacle was a penetrable ball, and he wasn't quite considering the behavior of the solution operator, but he was sort of bounding the scattered field outside the ball in terms of the incident field, but was getting these sort of similar bounds. So he was showing that this operation was bounded polynomially in K for, as long as K was outside some set where the measure of this set was small. Okay, so that's almost the end, but I just want to go back to then this numerical analysis error estimates that were the motivation for me for considering this question, right? So if we now go to the so this is exactly the same slide as we had before. Now the question is, what has our improved bound on C res? What does that get us? Well, so if we go to the HP version, so we've shown that at least when you exclude this set of frequencies with a set arbitrarily small, C res is now bounded polynomially in K. So now this means that P has got to grow logarithmically with K in the HP version, in the HP method, and this is great because this is actually what you see is required. So for the H version, then C res of K being polynomial in K, this somehow isn't quite so good. This still gives you bounds on H that are too restrictive from what you see. So there's still more work to be done there. But at least in the case of the HP finite element method and also the HP boundary element method, this bound on C res gives you somehow results that really do correspond with reality. Okay, so this is the end of the talk. We had this analysis question. We talked about why it's interesting for numerical analysis, and we had the answer. Here is the answer again here. And I'm noting that from the numerical analysis point of view, that perhaps the most interesting immediate corollary of this is that the HP finite element method and HP boundary element method are uniformly accurate under strong trapping, at least for most frequencies. Okay, so this is the end of the talk, and if you only remember one thing from this talk, make it that for most frequencies, strong trapping has a weak effect in frequency domain scattering. Thank you.
Very much. So yeah, questions for Euan? Okay, I'll ask a quick one maybe. So in your main theorem with David and Jared,
yes,
do you have any quantitative understanding of how the constant C depends on delta?
Yeah, no. So unfortunately, we don't.
Mm-hmm.
We don't. But that's an interesting question. I mean, I've spoken to some more applied people, and they've given me some kind of hand-wavy arguments that say it should be sort of exponential in 1 over delta or something, but there's nothing proved about that.
Okay.
So Euan, in the 1D case, I mean, a very long time ago, probably more than a quarter of a century ago, I wrote software to try to calculate resonances in the 1D case, and
okay,
the phenomena that you're mentioning, as you say, are I mean, what they call the resonance width shrinking as you go up the spectrum. It's kind of well understood. I seem to remember I've even seen a funny name attributed to something like maybe Fermi golden rule. Matthias Langer, who's there, would probably know better than me. But looking at this problem the other way around, suppose you had to calculate the kj's numerically, and as you said, you then have a serious issue, right? Because somehow the window in which you observe their effect is so narrow that it's very difficult to land right on top of it. I mean, there were some tricks that we had, and I'm just wondering, are there tricks that you have for calculating the kJs for large J that you haven't told us about here?
No, so I've never considered actually calculating the resonances, but I know that, I mean, as you say, there are lots of people in a large body of work that do this. I guess, and of course, yeah. I guess I can send you, if you want, the main references I look to when I want to know the things about this, but just in case you don't know them already, but I can send you some of these.
So I think as far as calculating the resonances as complex numbers is concerned, I think I hope I know most of the stuff, but okay. Yeah, if you, I wouldn't mind having your list of references as well. I think, but your kJs are not the resonance. They're not even really, if we're honest about it, they're not even really the real parts of the resonances. Somehow, you know, they're only they're not precisely defined, are they? Or are they? I mean, in 1D we would define them as local maxima of the spectral density. So that's how we would define the kJs, and then their relationship to what are actually the resonances becomes a little bit more hand waving. And the way that we tried to find these local maxima of the spectral density was not to calculate the spectral density, but to calculate the first integral of the spectral density. Because then when you have a sudden peak in the spectral density, instead of trying to find a very narrow delta function peak, you're trying to find where you have a step, and it's much easier to see a step than a peak.
Yes. Yes, I mean, on this question about the definition, I guess, I mean, I'm thinking about these kJs. Okay, the kind of terminology would be sort of that these are quasi-modes, and the real frequency of these quasi-resonances. And you have these results that if you have a sequence of resonances, then you have sort of sequence of, there are all these results, because saying if I have quasi-modes, I have resonances, if I have resonances, I have quasi-modes, and at least as k tends to infinity, the real these kJs are going to be super algebraically close to the real parts of the resonances in the limit k tends to infinity. But of course, this tells you nothing for fixed k, right?
Thanks.
So more questions for Euan. So this doesn't appear to be the case. So let's thank Euan again.
Thank you.